theory of LSH on how it's applied to like very new kind of settings. So thanks.
Thanks for having me. It's always a pleasure to speak in front of people who understand algorithms from deep inside. So, I mean, a little bit about myself. So what is keeping me busy since 2010? And again, like the question that I was fixated since the start of my PhD was how can we design exponentially cheaper alternatives for AI ML, and both from a compute and memory perspective, training, inference, all. And I'm looking for like, more or less rewriting how things are, because somehow I was convinced that matrix multiplication, the way it is, I mean, most kernels were written for matrix multiplication, it's going to hit a wall. And there were some instances even back in 2010 that there are reasons why they are very slow. So that was the prime motivation of what I've been doing things, and it got interesting more and more, and I continued. And as as already you have heard that in my pursuit, I have overused, or in some sense abused, two fundamental ideas. One is LSH, and the way I look about LSH is some fancy lookups and fancy hash functions. And I will talk a little bit more about what I mean by that. And also a lot of count sketches. So if you can design a hash function and then do some sort of a fancy aggregation, something very interesting happens, and mostly focused on machine learning perspective. So kernel density estimation, in general, like, weighted kernel density estimation, that is like for the estimation part, and LSH lookup for parameter and data selection, right? I mean, we just had a talk about matrix sparsification where there was some notion of selection. And I'm going to use a lot of like the ideas pioneered. I mean, Alex is here. So pioneered in by, the folks in LSH about how can we do some very interesting selection stuff. And on the top of it, over the course of time, I realized that if we are trying to rewrite fundamental ideas, we cannot rely on even the infrastructure which is designed and built to cater the existing narrative, right? So every infrastructure out there, I'll talk a little bit about it. I also have a startup which is called Third Eye, written Third AI. Actually, we have a saying that third eye is beyond open eye. So that's it. So, I mean, again, like in 2024, obviously, I don't have to convince you why this is important about thinking about like very large models. There is a very good trend that is going on in the machine learning community, and it's a very welcoming trend that over a course of time, it's becoming more and more clear that it's the size and scale and not the architecture. Right, so the famous paper, Attention is All You Need, if you read that paper, it's about making LSTMs obsolete. So they somehow argue that you don't need this LSTM kind of argument. You can get around it, and that is what the paper was actually written for. After that, there are a bunch of works that are coming up. They're saying, look, I mean, there's now a debate between convolution versus attentions. I mean, look, if both of them work, if you like convolution, go with it. If you like attention, go with it. And even starting now, I mean, it's not foreign that people are talking about, well, do we really need attention? I mean, there are talks about MLP mixers, and people are even showing that MLPs can do what attention can do. And the results are becoming more and more interesting. In fact, the largest neural network is actually Facebook's reported, like Meta's 12 trillion parameter, I think it's a DLRM model. And that's still the largest one, at least reported in the paper. And it's kind of a fully connected network still. Like they are trying to go towards attention, but that's what I've heard. I don't know much about it. But the moral of the story is anything reasonable and big is all you need, which is kind of interesting. One thing that's still, there is a subtlety in this that, look, I mean, if you think about GPT 1, 2, and 3, they are the same architectures. One is small, the other is big. So if there were really something in the architecture, you would have noticed something in GPT-1 or even GPT-2. But you really start to notice things as GPT-3. So it's actually the scale, right? The scaling phenomena, the large language models, the focus on the term large in the large language models. So obviously, what is not good is it's not sustainable. It's hitting a wall. We have seen several of these plots, so I'm not going to waste time on it. But I mean, these are some of the costs. And this is not a cost of like building a model from scratch. So this is a cost that after you hired a team, you invested in a lot of infrastructure, and you gave the team about a year to come up with their best model. Then they come back to you and say, okay, I now know the recipe of making GPT-3. Then you hit a button, and that's a bill you get. So it's pretty nasty. And again, like, what is a hope? So this is, a New York Times article back in 2016 that talked about the end of Moore's law. But there was one very interesting statement. There was that as the engineering progress slows, advances will come from human creativity. And I think it's in algorithms. I think this is, again, like we actually did this experiment with all the GPT models released by Meta. So they released a model from 350 million all the way to 170 billion. And what we did was we just run this model, and we want to know how many computation in this models are 0 or 0 times a number. That means wasteful computation. Just inference, because if you do inference, training is the same. If something is 0, it doesn't participate in the gradient descent. So we take this model, we run the inference, and we ask a question. These are the different layers. As you can see, small models are not very deep. The biggest model, 175 billion, is very deep. And I'm looking at, again, like I just use the word sparsity, and the sparsity 1 means there is almost all the computations are 0, and 0 means none of the computations is 0. And what we realize is this, that even for a 350 million parameter model, about 80% or more of these attentions or these computations are all 0, and they are exactly 0. And it increases with the model size. It increases monotonically with the model size. And in fact, as you go to 175 billion, more than 95% of them are 0. What does this tell you? That this tells you that the parameter has a memory, but it's very, very distributed. And again, like it's also one thing which was clear to us, that you cannot throw away parameters. Throwing away parameters is like taking away that large. Every input, like it's like a selection problem. So you have an input, and you have to select which parameter to use and only use that. Rest are immaterial. Similarly, in another, we looked at attention. And so one thing was that, okay, attention is very sparse. So you also see where it's very sparse. It's also very repetitive. So what we are trying to do here is we are taking a sequence position here, and this is like a GPT kind of a model. And we are trying to predict the next word, right? How the GPT works. Now, when you predict the next word, you show what the attention scores looks like. So what these plots are showing is that I am at token number 176, and I'm trying to predict token number 179. 176, and this is 180. Obviously, there's a gap in between. And I'm trying to predict the next token, and what is the attention score looks like. And by the way, the dark ones are only materialistic. The others are near 0. So these ones are near 0. Now, I do it at 176 level, but even if I do at 228 level, look at the position. Whatever the attention that was sparse here, it's the same attention that is sparse here. And it doesn't matter what you try to predict, which is also very much believable. If I have a prompt that I am visiting Musée d'Orsay in Paris, everything is deterministic from there, right? You can determine the whole next, maybe you're writing the whole paragraph, but it is you can determine it just from the context. So it's natural that these patterns are repeated.
So you increase the context.
No, so this is basically the context length. Okay. But you started from some prompt and you start generating. And when you generate, you figure out what the attention scores looks like. And what you realize is that it doesn't matter. I don't even know what I'm going to generate. But the attention score for these part are roughly the same. It doesn't matter where I'm generating. It's pretty interesting. Right? So, I mean, again, like what I'm trying to point at is that there is a lot of selection and weird patterns, but most importantly, a lot of computation is wasteful. Yes?
Doing 8-bit computation and many things are rounded to 0.
I think this was not doing any. I think maybe B float 16, but not more than that.
I guess I'm just wondering, like, if you're really doing like long precision real numbers, then everything will be a little bit non-zero.
I think that's actually a great point. So another thing I want to stress on the sparsity part is that in the previous one I was showing what things are exactly 0. But if you're doing low bit arithmetic, then things which are near 0 also become 0. So this problem becomes even more pronounced in low bit regime. So the moral of story is that there is a lot of wasteful computation. In fact, I have a friend at a big software company who says that we pay $500 million to AWS to calculate zeros. That's a reality of some of these calculations. Anyway, so where is the hope? And I think Wahab gave a very nice talk about selection. I think it's about this. See, there are two puzzles. I cannot compromise on size, so I cannot throw away parameters. So static sparsity and low rank, to some extent, is not looking promising, because low rank somehow argues that you can have less parameters, right? Effectively less parameters. So static sparsity doesn't work, but what we need is some sort of a dynamic selection. So imagine, right, so the world right now sits on matrix multiplication, which no matter what the pattern is, so imagine this is a billion parameter network, billion operation forward, error, billion operation backward, billions of updates, 3 billion operation per input. And if you look at this, out of this 3 billion operation, maybe 2.9 billion are zero. On the other way, if you could do something like, given a pattern, let's figure out what is relevant, only feed forward on those, back propagate on those, maybe we can get away in 50, 60,000 or 100,000 operation. And that should include everything, including the selection mechanism and the whole process. Now, this is what I'm going to talk about is like a dynamic sparsity. So parameter given the data. So I'm looking at dynamic sparsity given the input. What is the parameters that I should select and feed forward and back propagate? And again, like this is similar to the web analogy. In 90s, the web was as big as the neural networks of today's, and we never brute force the web. So why are we brute forcing these networks now? So that's kind of a thesis, but obviously there are connections with certain ideas here. Again, like lottery ticket hypothesis is one of the popular ideas, but it's still a static sparsity. It has shown a lot of promise that you could have a sparse snapshot of a network, but if you imagine that, well, every data picks its own data sparsity, then that is kind of stuff what I'm talking about. Mixture of expert is becoming another popular idea in which you're saying, okay, you know what, we get this, but we need structured sparsity. But what I'm trying to argue is if the number of experts grows very large, then the bottleneck becomes a gating network. So how do we get around that? So one idea is the sparsity of the model, and I think Wahab also talked about diverse selection. So the other idea could be, okay, so given data, you pick the parameters, but given the whole parameters, can I also pick the data? Because that's also interesting, right? I mean, I'm given the whole neural network. Think of a LLM as a query. Can I query the internet and figure out what data will be useful for LLMs, right? So that becomes like, and again, like the way it materializes is that there is a theory about adaptive sampling. So essentially, you're doing gradient descent, but nobody does gradient descent. People do SGD anyway. And then in SGD, you can ask a question, why do I take a random? Can I do something better? And if you look at the theory says that it should be the norm of the gradient, and it depends on the model. And we have shown some early results here. Okay. So now, selection idea, and then I'm going to talk about the tool that I use a lot, which is, I mean, again, like a lot of you know this, it's locality sensitive hashing. At a very high level, I'll say that it's, so everybody understands a hash function. A hash function is something that takes an input, could be a string, could be a graph, whatever, outputs a discrete number. And LSH are a fancy kind of a hash function. It's again like it's a randomized hash function. So it's a distribution over a hash function. Again, like sparing the details. You can argue that you can design some functions such that the collision of the hash agreement is monotonic in the some notion of similarity. So which is very interesting, because today if you come to me and say, well, my hash is 5, and 5 days later somebody else comes to me and say my hash is also 5, that kind of tells me that, well, maybe they two are similar without even I knowing anything about their similarity. Now, if you can design those functions, then that makes things interesting. For example, the way you can think about that is obviously you can use them in a hash table. So imagine this is your data set. These are just points. I'm going to take 2 LSH. 2 is just an illustration, nothing fancy about it. I'll create hash function 1, let's say 0, 0. Hash function 2 is 0, 1. And again, like my hash is only, let's say 4 bits for the time being. So I create a hash table and store this at a location 0, 0, 0, 1. And then I process the whole data point. Now, let's say I get a query and I have no idea what the query is. Okay. Now, what is happening here? If I take the hash 1 of the query and hash 2 of the query, then instead of like going and trying to compare this query with every other element, I can simply go and probe this bucket 0, 1, 1, 1. Because what this bucket is doing is this bucket, whatever elements are in this bucket, their H1 is colliding with the query and H2 is colliding with the query. So if collision is an indicator of similarity, then I have seen that indication twice in this case. 2 is just an illustration. Now, what is interesting about this to me is that data samples could be in billions. And just by 2 hash computation and a bucket probe, so let's say I take the bucket probe and even I take a random sample from that bucket. What I'm guaranteeing is that I'm getting something which is much, much better than random. So you can beat random sampling. And again, like I'm talking to a theoretical computer science audience, if you beat random sampling, 99% of your job is done. Rest is a gadget, is a probability theory. Now, this idea was something I'm going to use a lot. And the other interesting thing about it is that there are a lot of things. So first of all, I have a choice of how do I pick this hash function. Obviously, there is a whole variety of choices. But the other thing is I cannot just look at the elements and samples, so I can do some weird things in this bucket. For example, if I just look at the count in this bucket. So now you can think of this as a count sketch of the data with the hash function being an LSH. Now, what does this count indicate? It's an unbiased estimator of a kernel density. What is the count? The count is an indicator of collision and summation over all the data. If you just take the expectation, is the summation of the collision probability over the data with the query. It's a kernel density. It's an unbiased estimator of a kernel density because the collision probability is also kernel. And instead of adding the count here, I can do weighted addition too. I can say, okay, now this guy has a special weight. Let me not just add 1, but I will add some extra number for it. So I can compute weighted kernel densities. And I can choose the weights. I have a lot of choices over these hash functions. And I think there is a whole field out there. We can do a lot of things with this. So this is what was the things about most of the recipe behind what I have done. So I'll give you a very high-level illustration of the algorithm that I have been working with, and in fact implementing it through Third Eye, about like how do I train really large neural networks. So here is an illustration. So this is a neural network, and assume that the parameters are initialized randomly. So it's all random initialized parameters. Now what I'm going to do is, it is known, by the way, by the community, there was something called an adaptive dropouts. First of all, you do activations here, then you do ReLU. So you throw 50% of the activation. 50% of the computations are wasted. You compute the activation. If the activation is less than 0, you don't use it. In fact, there was a adaptive dropout paper in which it says that, well, it is better to actually threshold this at a much higher value. That means you only pick neurons that has very high activation and don't pick any other neurons. And in fact, you can sample it. Now, to me, this is interesting because let's say, imagine if this is millions of nodes, then the inner product of the node with the input is what determines the activation. The activation is always a monotonic function of the inner product. And that monotonic could just be the LSH monotonic. Why care about ReLU, GeLU, all those things work. Maybe an LSH will also work. So now what I'm going to do is I'm going to throw all these neurons into an LSH hash table. And similarly, I'll do it thus at every layer. Randomly initialized network. Random basis is a good basis. You start. Let's say you give me an input. I will only hash the input and go to, let's say, bucket number 3. At 3, I find neurons 1, 2, and 5. I'll say, okay, you know what? I will only compute activation of neuron 1, 2, and 5, and I will assume 3 and 4 is 0. I'll not even touch them.
Wait, can you explain this again? How are you hashing it into...
So this is an LSH hash. This is also an LSH hash. So this is pre-processed. So one time you do a pre-processing into a hash table. So one time linear operation.
And what is the vector associated with it?
So this is the weight vector associated with it, which is random for the for starting. And then this is the vector that I got. So I hashed this input, got to a bucket number 3.
So just to verify, so this is a complete, you're assuming it's like a complete bipartite network between input.
This is just a first hidden layer. It's a fully connected hidden layer. Yeah. So now I go to this bucket and bucket says 1, 2, 5. And again, it could be a fancy bucket. There could be 50 such hash tables and I am doing some weighted sampling. But basically, just by memory lookup, I'm deciding which neurons to touch and which not to touch. But my LSH is giving me a validation that if I pick these neurons, they are likely to have high activation. And I can oversample it. If I believe that I need 1% of neuron, I'll probably sample 5%. Still good. If I miss few, they are anyway going to 0. By ReLU, right? So if this was maybe a false positive, okay, go to 0. False negative, where there is redundancy in the data. I'll do the same thing. Now I have a sparse vector here. This is 0. This value I can calculate. I'll do the same thing for the next one. Now, same process. Now, what has happened here is just by hash computation, memory lookup, I have a sparse snapshot of a neural network. I'm going to feed forward on this, back propagate on this. And again, like some of the parameters might have changed. So maybe this weight has changed, this weight has changed. I'll go back and reorganize the hash table. What is noted, what should be noted here is all the computations I'm doing are of the order of the active neurons and not the total number of neurons. So if the number of active neurons is drastically less than the total number of neurons, this will still be efficient. And that is the idea. That is a cartoon. One interesting thing here is if you're doing a very sparse trading, then you can actually update in parallel. In fact, there was a theory of called Hogwild, which says that if you are updating neural networks and the norms of the update are very small, norms of the conflict are very small, you can as well update them in parallel. So gradient descent is sequential. I need to first know what my error on this prediction is and then update it and then do a prediction here. But if my predictions are not overlapping, I can just do the prediction and update. Now, I want to argue that this is for the first time to me, and I had a lot of conversation with Neer from MIT, who is a neuroscientist. The interesting thing here is, so we know that brain does sparse coding, like it has spiking neurons. Now, what is interesting about brain is, most likely brain does not spend any energy on neurons that is not spiking. Whereas all the prior attempts to do sparse coding were about, okay, let me probe you. Are you spiking? Are you not? And to me, sublinear algorithms are that bridge that may be what neuroscientists were looking for. Why sparse coding is still slow is because we don't do sublinear. None of the implementation of sparse coding is using a sublinear algorithm. But if you use a sublinear algorithm, for example, the neurons that I'm not touching, I'm paying zero energy for that. So that's also something which is quite exciting to me. At a very high level, this was also like this LSH is able to do this adaptive sampling. And I think there's a very nice analog. So let's say the puzzle you're given is given and fixed weight sampling. And you see I'm talking a lot about sampling and adaptive sampling. It's kind of a fundamental for machine learning. If you can sample well, you can do a lot of things in statistics well, right? So let's say you're given fixed sampling weights, W1 to Wn, and you ask a question, I want to sample I in proportion to Wi. The cost of getting one sample is order n, because I have to read the weights, create those intervals. And then subsequent sampling is order 1. Because I can simply flip a coin, see which interval I'm lying, and I'll sample that once I create that interval. So data structures and the amortized cost is order 1. But I think LSH gives us an analog even in a time varying situation. So imagine there is the weights, and these weights are changing every time. So imagine this, my input is the query, and the neurons that I want to sample, that depends on the query. So I cannot predetermine what the weights are, but they change in some form, for example, a monotonic function of the similarity. Then a lot of this sampling can still be done with some weights, can still be done in constant time, amortized. So this is, to me, was very exciting about LSH. And again, like as I've seen, like written like tons of ideas around, like, okay, can we do adaptive dropouts? Can we do importance sampling with gradient descent, kernel density estimation, compressed search? In fact, you can also argue that some of these sketches, combine it with count sketches and do like differential privacy on that. Now, on top of it, I was also like, okay, if I am building this idea, let's put it to production and make it to work. But as you can see, it required me to become a systems guy for a while. So I worked with a lot of people to build this hash table and like talk about cache efficiency and everything. So we wrote all this, obviously, several papers about, can we reduce that cost? Can we reduce data reading time? Can we do order 1 sampling? How can we exploit in parallelism? Again, like with one of my students, I was fortunate to be able to raise fund and create this startup. And so we started implementing. We got more hands-on implementing this idea. So we went to the drawing board, wrote everything from scratch. And we wrote a software for doing AI, ML, large language models only on like x86 processor. Nobody's solving that. That's the best place to solve, right? I mean, everybody will go GPU matrix multiplication route. Let's build something that could still work everywhere. And again, like some of the results that we were able to show is, and again, like this is a typical example that this is the running time and this is the accuracy climb. And so I'm not interested in when does a model reach a particular accuracy. I'm interested in the whole spectrum. This is what happens if you use, at that time, the popular package was TensorFlow. We were running it on 800. So if you use a CPU, obviously it's bad. GPU was much better. But then if you use this algorithm, even on CPUs, it was beating the GPU-based implementation. And this was written all in C++. And these are like, you need 4 A100 GPUs to run a 1.46 billion parameter model. This was some of the recommendation task. And we could run it on AMD EPYC because CPUs have like 6 terabyte. You can have 6 terabyte memory CPU. So I can actually fit entire GPT-3 on a CPU RAM. Not a problem. We spend a lot of time trying to get this validated. So there's a blog that was written on AWS ML blog. Recently, we have shown that you could actually take these GPT models and do fast inference too. And I think this is a huge opportunity. I mean, if I think at the machine learning stack, all PyTorch, TensorFlow, they were built for prototyping. They were built for researchers. They were built for prototyping, as in if I have an idea in ML, I can quickly get that validated. But when I see around, what are people struggling with? People are struggling with deployment. I have 5 millisecond latency limit. I have got 50 megabytes of memory, and I want this to work for 1 second latency at a millions of users at this scale. That is what most of the companies that I know, not like Google, they have a different infrastructure. But most people are struggling with that. And I don't think they have an alternative. So for them, it's like build something with PyTorch TensorFlow, then hire a team of engineers who will keep hammering it. And good luck with that, because like I mean, the statistics says that 80% of AI project never makes it to production. So why can't we flip it? Can we build like a production first software stack instead of building prototype? Let's build for production. Give me best AI that meets latency, cost, and deployment constraint. Can I build a software? So that's what I'm focused on. Obviously, there is a story about so if you look at, by the way, here is an experiment you can do with PyTorch TensorFlow. Go take a big model, make 99% dropouts. So do 99% dropouts. But ideally, 99% of competition you are throwing away. You're telling the model, I don't want 99% of the competition. You will actually see that the model slows down. The training slows down. Why? Because it will first do matrix multiplication, and then it will apply a mask. Everything is fundamentally built for matrix multiplication. And if we have a different idea as an algorithmist, then maybe we want a different kind of an implementation too. So we have to work with systems people and build this. We were able to get it deployed. And finally, like in last 5 minutes, I'll talk about, I think there is something which is very exciting to me is how can we go beyond like embedding for retrieval augmented generation. So right now, like everybody is interested in building domain specialized LLMs, like LLM or chatbots on my data, if you have heard of that. The idea is good old semantic search, and then you prompt an LLM. Okay, so the idea is, okay, does my organization provide retirement benefit? ChatGPT will have no idea. How about can I retrieve relevant text from my rule book or my database, provide this to ChatGPT or Gemini with that question, and it gives the response. Pretty good, right? I mean, that works. The problem now the world is struggling is they have a lot of data. Everybody is taking text, getting them embedded, and then going to vector DB. Let's just do a rough calculation. 100 million sentences, 1,000 dimensional vectors. That's already going into like 400 gigs for embedding. Another 400 gigs for vector DB. Just for 100 million sentences. Another issue is, let's say if you ask this question and you realize, damn, the model forgot Roth IRA. What do I do? Well, the standard notion is go fine-tune this embedding model, quote unquote fine-tuning, it will fix your ranking. If I change this, I have to rebuild this, recalculate this. So every time my model makes a mistake, I have to go rebuild everything, and they are still doing it. Well, why is this so? Again, as an algorithmist, when I think about it, I realize people are reusing. So somebody build LLM for you, and you are like, okay, nobody will build LLM. Let's just reuse what is there. Let's hack an embedding out of it. So this is like patching things to make it work. What is an AI first approach here? If you look at the pipeline, I think of this as an encoder. This is a decoder to a pointer, and a pointer goes to a text. I mean, we are computer scientists. Everything is key value. At the end of the day, this is pointing to few keys that is getting a value. Encoder, decoder to few keys, then goes to the value. Why do this contrived approach? If neural networks can generate next words, they can generate code, they can surely generate 3 keys. And that is what the learning to index approach is, which basically takes a neural network and just generate those 3 pointers. And that goes to here, right? I mean, and we showed this is to be superior. This is an AI first approach. Actually, you can use count sketches in the output layer if your output layer is too big. We showed that in 2019 on 50 million data sets from Amazon. And there are a lot of follow-ups. But this is what we can do with this. So this is the largest MS Markov benchmark. And if you use Elasticsearch, obviously that's keyword based, so key value pair, very fast, not very accurate. You can use some of the foundation models. The issue is, if you use low dimensional foundation model, you will need 26 gigs just to store embeddings. It will require you to have GPUs. If you use OpenAI's embedding, it will take 54 gigs to store the embeddings, another 54 gigs for VectorDB, assuming you do it optimally. An embedding will take day with their rate limit. We can get to this accuracy in 4 minutes on Mac with 16 gigs of RAM. So, and again, like the important part is fully private and air gapped. And the reason, we are not storing any embeddings. We don't have a single embedding. Anyway, I will stop here, but hopefully I have convinced you that, look, the problems that we are trying to go towards, hopefully I have argued you that how the world is fixing things. They are just plumbing things around. The world needs more algorithms than ever. However, the problem is they also cannot understand proofs. So now, but then this is also an opportunity. We can show it to them. We can show something. And we have been riding on hardware acceleration for a while, but likely hard to keep it up. And to meet exponential demand, we need to go to the drawing board and rethink all the gradient descent algorithms. Look, these algorithms were designed in the 80s, where we had 5 samples and we were asking what is the best way to use this sample. So neural network, backpropagation, great, works. We never changed from there. The whole infrastructure, everything is built to cater to those ideas, which is fine because that brought us this far. But where do we go next? Hopefully, I've shown you that randomized algorithm seems a very promising approach. And again, just from what I have been realizing over time, that if you are rewriting fundamental ideas, we cannot use existing infrastructure to demonstrate its value. Maybe we still have to work with system folks and rebuild the infrastructure too. So that was some of my attempts. Thank you.
Questions?
Alex, a more technical question. This you were contrasting CPUs versus GPUs and saying, like the natural interface works for CPUs. Have you thought about combining in a sense? Can we speed up things on GPUs?
So, I think, yes, we can. So the way we are trying to win this battle with CPU is we are not using the same architecture. So my first slide was architectures do not matter. So the way we are thinking about, especially even in building these software is, let's say if I have to rebuild an architecture with maybe dynamic sparsity, but obviously size and scale matter, what will that architecture look like that I want? Right? And the world is getting comfortable with it now. For example, nobody knows what GPT-4 architecture is. Everybody uses. We don't even know if they're even doing transformers or maybe if-else. Who knows? So now, if that is the case, and you have to win, because at the end of the day, it doesn't matter whether you're beating a llama or some other model. People care about like the end-to-end accuracy. So in making these modifications, so some of the works that we have shown before was a head-to-head comparison that this architecture, this. But later we realized if you have to solve a task, you just build one architecture that can solve all the tasks, like the LLM way. So we are not, I think what the interesting question there is, if we rethink algorithms, then we want to rethink architectures too. Now, coming back to your question, can we apply this on GPUs, right? Let's say if I can make one architecture better, can I run it on GPUs? I think that's an interesting question. I know there is a group at NVIDIA that was trying to build hash-based algorithms for GPUs, but the fact that everything is very randomized and random access, that actually kills a lot of advantages of GPU. Because GPUs likes the memory coalescing and all the simple parallelism. If you ask it to reroute the memory Maybe with memory reorganization, and maybe with more algorithms, you can actually get towards even with GPUs. But that's a great question. Yeah.
What's the largest model that you've built with what type of capability so far, like in terms of
So I think largest we did was 7 billion, and the 7 billion is what next word prediction. So it's a kind of a version of a. So it's not yet fine-tuned, but we could pre-train it on C4 data set on like 30 Sapphire Rapids or something.
So, and it's like a general purpose thing that like works well and across many evaluations. And how does it stack rank with?
So yes, so we have. So I think look. So the piece that we haven't done so far is the instruct fine-tuning. But what we have understood is if we pre-train, it get all those zero-shot capabilities that is needed. With fine-tuning, it definitely beats on certain tasks. Not on all right now, because obviously it requires a lot of training. And we are right now not, at least through third eye, we are not hyper focused on training a foundation model because everybody has one. We are focused on like task specific ones. But we believe you can do like if with enough resources, I think you can do pretty much anything. I mean, if you can train a 7 billion parameter, so we train
Resources.
I think resources means hammering, essentially. So I mean, again, like the dirty secrets of building an LLM, right? I mean, read that meta paper, even if you have a C4 data. So first of all, you need pre-training. Pre-training is on the C4 data. Then comes fine-tuning, and nobody talks about what data they fine-tune on, right? And nobody will talk about it because that's where most of the secrets are. But given what we have seen with the capabilities, if we get those secrets, or if we learn those secrets over time, we should be able to build it too. Because I mean, there's nothing here that is not there, or there is nothing there that is not here, right? I mean, it's all about gradient descent, maybe sparse gradient descent, and large models.
Go ahead.
So in your slide, you had these, like when you had these neural networks, you were constructing the hash table, right? How do you get the values to be hashed? How do you select the neurons?
I don't select the neurons. So essentially, the neurons are like randomly initialized. So let's say I have this neuron. This neuron has a weight. I compute the LSH of this weight. Let's say it comes out to be 3, it goes to 3. This one, the LSH comes out 3, goes to 3. This one, the LSH comes out to 2, goes to 2. This one, so that's how you do it. Similarly here. And again, like these are not one table, there are multiple tables, like a typical LSH sampling scenario. You want to get multiple table, do weighted aggregation, do something very simple, very cheap and dirty, because you don't want to spend a lot of time, because this is something you will do a lot of time. And then you do data parallel. So every data comes in a parallel thread. Every thread goes forward, does this, back propagate and update, overwrite if there is some conflict, and it still works. So neural networks.
This is related to actually your answer to Alex's question. So one of the issues often with like sublinear or sampling-based algorithms, right, is that they're basically cache non-local. So sometimes you can have an algorithm which is actually linear or even superlinear, which beats a sublinear algorithm in practice, just because the cache locality of just doing passes over the data is much better.
So I think this is a great. In fact, one of the line of work. But by the way, one of my students who's going to be postdoc here at Berkeley now. We worked on like how can we take universal hashing and make it cache efficient. And what we realize is most of the problems with randomized algorithms is because we take one element and go to one element. But instead, if you do contiguous chunk and go to contiguous chunk, so you force yourself that you will read a contiguous chunk and map it to contiguous chunk. So what we showed was a few papers in MLSys. In fact, we were able to beat the MLPerf benchmark by compressing the biggest MLPerf for that DLRM MLPerf that they have on a terabyte data. We were able to compress it in 10 megabytes of memory and still get the same training time, more or less. And obviously, inference was 3x faster. But the idea was, I think this is also a great point that has been brought up, is when we build these algorithms, we don't care about how they will be implemented or system efficiencies. So maybe a line of work that I think would be very interesting is, if I have an LSH algorithms on all these, how do we implement it on GPUs? And I think you have to figure out ways to do these cache localities. So maybe don't take then it kind of like, so instead of saying like, okay, if my memory, this is laid out contiguously, I maybe not want to store these two differently. Maybe I want to treat them as chunks and force them to be together. Now, the good thing about learning is even if they are not together initially, the learning will, if you force them, the learning will figure it out how things should work, right? I mean, it's like anchoring. You're saying, okay, I cannot treat them differently. They have to go to the same location. So that then it kind of becomes a little bit like a mixture of expert, if you may start thinking about it. But yeah, this idea that you need to get cache locality in randomized algorithms is, I think, one big barrier that we have to overcome in implementations. But again, like there are ideas around it. Like, so, I mean, in general, like a standard universal hashing, what we realize is, in fact, it's better for variance. So what we showed in that MLSys paper is, if instead of doing universal hashing for dimensionality reduction, if you take a chunk and map it to a chunk, it's better than for inner product variance, and it's also cache efficient. So you can get best of both worlds too. But that's a great question. Yeah.
Okay, if there are no more questions, let's. We'll reconvene at